In my opinion, they should not be called accumulator functions. In my opinion, they should be called integral functions. Do you remember how way back in like February, I defined a derivative as like the derivative at a point, which is like a limit, which is like a number, right? And then with like a pause of 2 minutes, I jumped right into the derivative function. What is the derivative function? It's a function which outputs derivatives. Similarly, we have been spending the last week talking about integrals. What is an integral? Well, it's a limit, which is therefore a number so far. Okay, so now we're expanding the concept of an integral in the same way that we expanded the concept of a derivative. This thing that everyone calls accumulator function, so I'll call it that also, is a function which you give it an input and it outputs an integral. So in some ways it's like an integral function. And the way you do it is, like, you just do it. These are all like lines and circles, so you can just like, everyone just doing it with geometry. So I get 0. Is everyone getting the same thing I'm getting? It's like that little guy over here has area 4, and then it's like from -4 to 3, so then you get like a -1/4 circle. Are we cool? Okay, and then this last one is going to be that, plus now I add another, that triangle has area 2, and that's like a 3 by 4, so that's 12. So I guess that's 14 more than this one. Did you get 18 minus 9 pi over 2? Yep. Okay, is everyone cool? Okay, so if you made it this far, I'm sorry if I'm rushing you a little bit, then that means you understand basically what an integral function is and sort of how it all works. Are we cool? Anyone have any clarifying questions? You need a clarifying question? Or you're like already like doing the bottom? Okay, the bottom asks a whole bunch of leading questions, which if you can answer them all, you suddenly start to think, damn, something's really going on there. So instead of, I could just give you time to sort of talk them out with yourself, but instead, maybe we should just like kind of jump in. All right, let's go. This function g says, start integrating at -4 and stop at x. As x changes, we accumulate more and more area under this curve. So let's kind of like ish. You're saying ish because when you have negative area, it gets a little weird. Okay, yes, I agree. Woo! Okay, so let's start kind of drawing some rectangles and like talking out what happens. This is the key moment. Everyone like, look up here. So I'm drawing a little rectangle now. What just happened to G when I drew that rectangle? Annika, what just happened to G when I drew that rectangle? Did G get bigger or smaller?
Increased.
G just increased, right? Because G is just the integral from -4 to x. And if I just drew another rectangle, then G just got bigger. Okay, what happened to G now? What's happening right now is I'm letting x increase. I'm slowly moving to the right. What just happened to G? It got bigger. Okay, wait, I'm going to draw another little rectangle. What just happened to G? It got bigger again. How much did it get bigger?
More.
That was like, is it getting bigger at a constant rate?
Yes.
No, I don't think so, right? Because this second I added a small rectangle. but the next second I added a bigger rectangle, and the next second I added a bigger and a bigger and a bigger. Okay, so wait, this is the key moment. What about now? What about when I draw another rectangle? Now what just happened to G? It got bigger, but a little bit slower because I added a little bit less. Okay, now when I add one of these like short little rectangles, what happens to G? It got bigger, but even slower. Okay, and finally, yeah? Okay, now, what starts happening when I start adding negative rectangles? As we learned last week, negative rectangles like contribute negatively towards the Riemann sum, so now G is decreasing. And now, every time I add one of these negative rectangles, G decreases. And by the way, what controls the rate at which G decreases? Like how negative it is or something like that, right? When it's like a big negative rectangle, G decreases a lot. But when I only add like a tiny negative rectangle, G increases less quickly because I only made it a little bit more negative. Okay, now we're back over here. Now I add another little rectangle. What just happened to G? It got bigger. And now if I add another little rectangle, what just happened that second? G got bigger, but it got bigger by at a faster rate because I've added in a taller thing. Okay, how about from 7 to 10? What can I say about G on the interval from 7 to 10? As x moves to the right and I add rectangles, it's increasing, and at what rate is it increasing? A constant rate, because I'm adding a constant amount of rectangles as we go. In fact, the rate at which G increases is precisely the height of the rectangle that I add. The rate at which G is increasing is whatever the value of f is at that moment. In other words, if I take some function starting at, it doesn't matter when, and ending at x, and I have some function f, and I define some function which keeps integrating until we tell it to stop, then, and now I ask, not just whether this function is increasing or decreasing, but what is the rate at which this function is increasing? What is the instantaneous rate of change of this accumulator function? In other words, how fast at any given moment is this integral function gaining new area? And the answer at any given particular x value, or how fast this is gaining area, is just whatever f is at that moment. So they like cancel, man. Yeah. The fundamental theorem of calculus says that the instantaneous rate of change of an accumulator function just is the value of the function that you are integrating. In other words, the derivative of the integral of a function is the function. Whoa. Okay. What do I have left? Like 2 minutes? 1 minute? This has been immortalized in a piece of artwork which I commissioned 6 years ago. This painting is entitled Fundamental Theorem of Calculus. And here's what's going on. I probably don't have time to explain this. I'll try and I'll do it again tomorrow. Here we have an irregularly shaped room. And because this room is irregularly shaped, notice we're inside the room and we're looking out the window. So the far side of the room has this kind of sinusoidally kind of weird thing. So if you are going to install hardwood floors in such a room, you're going to have a lot of work to do because you can't just cut equal length planks. You need to cut the planks to be of all different lengths. So you hire a superhero who hangs from the ceiling like Mission Impossible style, flinging floorboards down at the rate of like 4 or 5 per second, landing perfectly along the room such that it's flush with your irregularly shaped wall. And really this only takes them a couple minutes. It's very expensive. You check in halfway through the process. What you see here is the floorboards falling. Person hanging from the ceiling not depicted. And the question at any given second, at any given point along the room, if you walk in and you ask, at what rate is this person finishing the job, the rate at which the area of the floorboards already laid is increasing is whatever the height of the floorboard just laid. However long the wooden plank that at that moment they dropped to perfectly match the length of the room, whatever the height of that floorboard is, that is the rate at which we gain area of the person sort of doing the job. Follow? Woo! That is the fundamental theorem of calculus. There is a handout. Sorry, I forgot, and then I remembered. It is right here, take one. It is a problem. It is doing an integral. Why is it messed up? If you are a serious person, you will put your party hat. I don't know what you're going to do with it, but bring it back tomorrow. There will be more festivities tomorrow, and there will be additional dumb things like bought at the dollar store. I was going to bring food tomorrow. Bring food tomorrow too. Part 2 tomorrow. Can't miss it. Someone turn the camera off.
Is it like, oh, it's still recording. It is still recording.